Hi, my name is Steve Ward, and this is an introduction to SQL databases. Before we start, a bit of information about SQL databases. These can be called Relational Database Management Systems, or RDBMS, but they're also known as SQL or SQL databases because of the language that's used to query them. So SQL stands for Structured Query Language, and there's a lot of standardization of what was previously SQL into SQL. And there's also a lot of standardization about how the relational database management systems work. Now, SQL or SQL databases, they first came around in about the mid-1980s, and they've been enhanced over the years, and now there are multiple databases which can be used for different purposes. But the common ones I'm going to be covering are things like Microsoft SQL Server, MySQL, also known as MariaDB, you've got Postgres, SQLite. There are also bigger, more commercially oriented databases such as Oracle, and then there's a whole load of new databases these days which don't necessarily use SQL, such as MongoDB and some other databases. And also there are plant historians. So if you're in the industrial automation world, a plant historian is a high-speed database, but it maybe doesn't use SQL in order to query the data. And the reason for that is in a historian type database, you're really looking at time series database and time series data where you're storing tables and then you're storing the data and the index is always time. So maybe every second you store a value, or maybe every millisecond or every few seconds, but they're very much organized around storing data in terms of time. But when we look at an SQL database, it's really about storing values and parameters, and then they can be indexed. And there's a lot of aspects that come into it. So I'm going to try and cover that through the course of this session. I will use SQL and SQL interchangeably, but generally these days you really should be referring to SQL because that's the industry standard. So let's start with a formal definition of what is a database. A database is either, or both of, a collection of data that is stored and retrieved. And that's important. It's not just enough to store the data, you must be able to retrieve it as well. But it can also be the application that performs that storage and retrieval. So as mentioned, this is often what we refer to as a relational database management system, maybe an RDB, relational database, where DB is the database part. RDBMS, you might also hear of, which is a relational database management system. But typically these days, people just call it a database. Now, a database may be a very simple set of data or very complicated. You could argue that a simple list of values is a database, but so is a complicated customer relationship management system. They both store data, there's an application which manages the data, and then there is a way of retrieving the data. And again, these database applications, they can also be simple or complicated, as we just discussed. So SQLite is a very simple file-based database. It's barely a database application at all because your high-level application embeds the SQLite API and just reads and writes directly from the files. But within those files, you can do the SQL queries, so it is a full SQL database, even if it's more likely embedded inside another application. Now, we get a lot of open source databases these days. MySQL, MariaDB, Postgres, they are very popular. They're popular because they're relatively powerful, but they are also free. However, my view is not everyone wants a free database. One of the issues of a free database is who do you sue when something goes wrong? So I do find that in some big organizations, they would rather pay money to get the expertise and also to have a backstop in case anything goes wrong. So the two biggest databases today are Microsoft SQL Server and Oracle. They have about 30% market share each, and they are used for both small applications, although less so Oracle, but you see them a lot inside enterprises and you see them a lot in large applications as well. There's also a big move to the cloud these days. So there's SQL Azure, which is Microsoft SQL Server in the cloud. And with these other databases, you can often rent instances of those databases in the cloud as well, using AWS or Microsoft or whoever your preferred cloud vendor is. Now, I mentioned time series databases for historians. We are seeing time series databases being adopted. The two common ones there are InfluxDB and Timescale. Timescale is actually a development of the Postgres database, and it includes some time series elements which make it suitable for high-speed data storage. And the reason high-speed data storage is important is, particularly in industrial applications, you might have a huge data set that you want to store. So for example, consider a gas turbine. It's rotating at something like 3,000 or so RPM. It maybe has a set of several gas injectors and there's multiple temperatures. And what can happen is that turbine can run away very quickly if anything goes wrong. So to be able to control it and to be able to do post-trip and post-fault analysis, you need to be able to store all of that data very frequently. And you might find in a gas turbine, for example, there could be a megabyte or more of data being stored every second. So that time series database with lots of high-speed data storage becomes very important for those applications. Now, above that then, we also get complicated database applications where it's no longer just a database now. It's actually an application by itself. So Salesforce is a good example. Salesforce is a cloud-based application. It's got an underlying SQL database, but what the user sees is a customer relationship management database. So it's a customized form of a database designed to solve a particular problem, which is customer relationship management. SAP could be a similar one, which is used for enterprise resource planning, and there are probably multiple other ideas and options around this as well. So in this deck, we're going to cover SQL databases. I might cover high-speed databases a little bit. So for example, with Postgres, like I mentioned, with Timescale, there's a big overlap between Timescale and Postgres. By the way, I talk about Timescale. Timescale has now been renamed as Tiger Data, but Timescale and Tiger Data is the same thing. Generally though, when we're talking about a database, I'm referring here to databases which are based on a structure and which you can query the structure using that structured query language. So what is that structure? Well, what's inside the database is a number of objects which are configured in what's called a schema. So you'll hear about database objects and a database schema, and the database itself covers all of those objects together. So the fundamental aspect of a database is a table. A table, the way to look at that is very similar to a spreadsheet. It consists of rows or records and columns, and within that table we store one or more items of data in a row, or a record, and then each time we add one, we're adding different data elements and they are stored in the columns. So for example, if you thought of a typical data logging application, you might be logging the time, that would be one column. You might be logging the tag name, that would be another column, and you'd be logging the data value, that would be the third column. And in each row, you would have a record which consists of that item of data, which would consist of the timestamp, it would consist of the tag name, and it would consist of the value at that time. And of course, as time goes by, you would build up those rows, so you'd have multiple rows covering those columns, so you'd be able to do some analysis on that tag name set of data. So the table is the underlying aspect of the database which stores the actual data itself. Now, tables can be quite complicated, and it's also possible to have multiple tables which can be linked together. So what we can do is we can have a view or query which allows us to either have a subset of a table. So for example, you might have a subset of a table which takes all of the data for a single tag name and just gives you all of the timestamps and the data values for that tag name. So if you're storing multiple tag names into a single table, that view could be a simplified view for that one tag name that you're interested in. Conversely, a view or a query can also be complicated. If you've got a complex table with multiple linked fields, which is possible, you can actually build up multiple tables together using keys, both primary keys and other keys. But I'll come on to that later maybe. But the idea there is that view or query could consist of a way of joining all those tables together so that you get a simple view of what they are. For example, you might have one table that's storing the tag name, you might have a linked table that's storing the tag name's description. So a view or a query could give you a single result that gives you, from the previous example, it gives you the time, it gives you the tag name, it gives you the data value, and it also gives you the tag name, the tag description, which comes from that linked table. Now, in industrial automation applications, we don't always have views and queries in the database itself. Often they will be created at the application layer when we do a report or when we're putting the data into a table on the screen, or maybe even onto a trend. Now, there are other things we have. We can have procedures or macros. These are automatic operations. So for example, you might want to clear up the database and you might want to delete anything that's older than a month every day. So that might be a procedure or a macro that queries the database and deletes data that's older than 30 days. And you could run that procedure or macro every day, and that would stop the database from getting too full of data. There might be other procedures and macros you could do as well. Maybe you want to average the data. Maybe you want to do a complicated calculation or analytics. So that procedure or macro, that might be a way of doing that inside the database. It's also possible to have these procedures and macros running outside of the database. So for example, in the industrial automation application, you may query the data using a script of some sort, and then you might do the calculation in the script. So those macros and procedures, we are referring here to specific operations which are inside the database, but you can also do those operations outside the database. And in some cases, you might do a combination of the two. So you might be using procedures and macros for some data summary applications, and then you might be using an external script to do a further level of analytics. So try not to confuse you here too much, but it's certainly true that these applications can become very complicated. Now, in our table, we need to restrict what information can be entered and possibly viewed, but certainly what data might be entered. So we can also have rules. So for example, in your table, you might want to restrict the date and time format. Maybe you don't want milliseconds, so you might have a rule that says we only store the seconds value as a minimum, although you can also do that with the table definition, so maybe you don't need a rule for that. But whereas a rule might come in, you might have a rule that says, we can't have any data that varies by more than plus or minus 5% from the previous data item. So you might have a rate of change rule. You might have a value or a rule that says, we don't accept values greater than 100%. So those rules can be business rules, or they can be data integrity rules, and they can define what data can be entered into the database. And this is a key point about databases. We need to make sure that the data inside has its integrity preserved. So defining those rules can be an important way of ensuring integrity to begin with. Another aspect is null values. Maybe you've got a value, so you've got the tag name, you've got the timestamp, but maybe that data value hasn't been collected, so it has a null value. So one of the rules might be, will you accept null values into the database? Maybe you will, maybe you won't. Often that's why these are called business rules, because they're defined at the business level. But you have these rules to limit what data might go into the database. I would say null values, you often don't want those because there isn't a value there. But there are occasions where null is acceptable. For example, you might have a system where you've got the computer name and the username when you're logging an event. But if no users logged in, you might log null for the username, but you still want to know the computer where the activity happened. So there are occasions where null is allowed. But also there might be occasions, particularly with data, where null is useless and it can affect your analytic values, so maybe you wouldn't want it for that. Now, I mentioned these tables can get very big, so we can index the tables to allow faster retrieval of data. Now, if you've got all your data stored in a time series and you're populating your database table in time series order, there's a good chance the database is already going to be highly ordered to begin with. But if you think of a CRM example, it maybe isn't ordered in that way. So you might have a list of customer names. So what you might want to do is you might want to index all of your customer names alphabetically from A to Z. And the reason for doing that is it makes it much faster to find your customer name, because instead of having to search through every single entry in the table, you can just go directly to that table entry via the index. And what you do is you sort the index itself rather than the table, and it makes it much quicker to find the values in the tables. Now you might say, couldn't we sort the table itself? Well, yes, you could, but imagine you've got a table of 10,000 entries and you insert, using a CRM example, you insert someone whose name begins with M. That goes into the middle of the table. Without an index, you would have to resort that table. You'd have to move several thousand entries just by one so that you can make a new space to install that new person whose name begins with M. What we normally do in this case is you'd actually just put the person's name beginning with M at the end of the table, and it would be your index that's sorted, and it's much quicker to sort the index than sort the entire table. So that's why we use indexes, allowing faster retrieval of data. Now, as I mentioned, in a time series database, indexes aren't so important, but as soon as you've got data that's indexed by other criteria, indexing is extremely important to tune your data. And in many cases, if you find your database is running slow, then working out what is indexed and what isn't is a great way of improving the performance of the database. However, you need to be careful not to have too many indexes, because when you insert data, you are sorting the index, and the more indexes you've got, of course, the more that takes time. So you might have faster retrieval of data, but you run the risk of reducing the speed of inserting data into the database. So there's always a trade-off between which is best and how many indexes to have, but certainly indexing is a good way of improving that performance. The other thing we have is relationships between the tables. Now again, if you've got a simple time series table, then it's already sorted, and there's a good chance you just have a single table, and each entry goes in there with its timestamp, its tag name, its value, maybe some other metadata, but that's it. But think about it, if you've got a table like that and you're also inserting the tag description every time, you're going to have a lot of duplicated data. So this is where the idea of linked tables comes in. So what you would do is you would have a table with the tag name, and then that tag name would be a key which goes to another table, and in the other table you would have a foreign key value which would be your tag description, and that would be linked back to your first table. So it reduces the amount of data storage you need to have because you only store that tag description once. However, then you have to link the tables, and that's where these relationships between the tables comes in. So you have a relationship where you do joins, and you have multiple tables, and you have these primary keys and foreign keys and other key values, and that's how you link all of these tables. And then the final thing you might have in the database, you might have reports. This might be a report for the data, depending on what database type you're using, but there might also be reports on the database structure. So a good database system will allow you to produce a report which fully documents what the database looks like, so that it's easier to recreate in future if you need to. Now, of course, you would also back up the database on a regular basis, and you might just want to back up the indexes and other things, the ones that change the most often, but equally, you might also want some database documentation, and that also might be useful if ever you maintain the database in future. So those reports, that can both cover your reports of the data, which are used by your users of the data, but it can also cover the database, which is used by your database administrators and creators and so on, both for creating the database, replicating the database, and maybe maintaining the database in future. So there's a lot of complexity here, but the key boils down to is you've got these tables, that's the key part. You might have procedures or macros, you might have rules, and then for performance, you might need indexing. But in a simple application, you don't need all of those. A very simple application may just consist of a table, a single table. So for a HMI SCADA database logging application, for example, that's all you might need. It's just a single table with your timestamp, your tag name, your data value, and that's it. But of course, over time, then that can grow. If you want to include additional values, maybe you want to do analytics, maybe you want to clear out old data. So all of these other things can be added on when needed. But as a minimum, you would need at least one table. Otherwise, there's no data without a table, and with no data, it's not a database. So let's cover that table structure in a bit more detail. So if you think about it like a spreadsheet, you've got a row which is going horizontally, and each row is a record. So a record consists of a single item or collection of items of data which makes up whatever you're actually interested in. So for example, like mentioned earlier, in a HMI SCADA application, you might have a data item which would be the tag or the tag name, it would be its data value, and it would be the timestamp at which that data value was recorded. And that's a single item of interesting and useful data, and that would be a single record. And there would be multiple rows or multiple records as the table brings up. What you've also got is the columns. They also consist of those data items, but now you've got more of the vertical focus. So you've got the timestamp. That would be, for example, a time and date data format. You might have the tag name itself, which would be a string. So probably a string or a varchar, and there's different ways of representing strings. A char type here or char is just a single value, whereas a string is more flexible, or varchar is multiple characters. So you'd have to look at the database documentation to see how this works for your particular database. And then for the actual value for the tag, you'd have the numeric value, which might be integer, double integer, real, or float, and so on. So formats do vary from database to database, but effectively you define the structure of that database table by defining what the columns are, what the data format is for each of those columns, and then when the table is built up using insert instructions or append instructions, I'll come on to that later, then that's where the actual table contents are built up. So here's an example of what a HMI SCADA data log might look like. In this case, we have one value per record, which is generally more efficient for point or data storage compared to recording multiple values per record. But it depends on how you log it. So one of the key points about databases is if you're a database purist, you want to eliminate any duplicated data, and you might also want to reduce the size of the database as well. However, those are very much things that come back from the 80s and the 90s when disk space was expensive and CPU performance was slow. These days, you often have to optimize your database, and you might have to decide which do you want. Do you want most efficient for data storage? Do you want most efficient for data retrieval? Or do you want some sort of balanced approach? And they are not mutually exclusive, but they are very different in how you would implement your database. So here is a typical data log for storing data. So we have a unique ID, so this would be like your primary key. So the reason for having that unique ID is that we can identify individually every record that's in the table. You don't need this, but most databases will have this just because it's good practice to have that ID field. And also then if you're linking tables, the reason for having an ID field is that ID field becomes how you can link to another table without having to put in additional data. So it can improve efficiency across multiple tables if you've got these link type databases. So in this case, we've got the ID, which is optional but useful. But we've then got the timestamp, so this would use a particular date format. Then we've got the point name or the tag name we're logging, and then we've got the point or tag value that we've logged. So in this case, we're logging at 12:01, we're logging 3 points. We're logging log point 1, log point 2, log point 3, each with their individual value. And then at 12:02, 1 second later, we're logging log point 1, log point 2, log point 3 with their values. And notice not all of the values have changed. So log point 1 stays the same, it's still at 100. You could argue here, do we need to log point 1 again? Well, again, that would depend on your application. So from a database purist point of view, the fact that we're logging multiple values for log point 1, which haven't changed, from a database purist point of view, that's a bad idea. But if you had something like a 21 CFR 11 application where you want to see what the previous value was, this could be a good thing. So it's not just the data storage element, it's also about the compliance or the application you're doing. And from a trending point of view, if you are retrieving all of these values, it's probably more efficient from the trender to retrieve one value every second and plot that value even if it hasn't changed, than have to have the trender extrapolate from, say, the previous log value to the current value. And then you also get into issues about what happens if the change is quite big. How do you capture that spike if that spike happened over a long time? Do you interpolate linearly, or do you have some sort of spike logic? So this is a common way of overcoming a lot of those issues. Yes, it uses a bit more disk space, but let's be honest, disk space these days is pretty cheap. So in this case, this is a good way of having efficient data storage for multiple points, as well as having compliance of being able to understand what was the previous value if it changed. And from a human readability point of view, this is pretty good. And also from a query point of view, this is quite easy as well, because if you wanted to just query for all of the log.1 values, you can use what's called the select command that we'll come on to later with a where clause, and then you can just easily use the where point name equals log.1, and you can just bring back all the values for log.1. So this has a lot of benefits and advantages. And what you can also do is you could extend the number of columns. So you might have previous value in there as well for your 21 CFR 11 compliance. On the timestamp side, you might have both UTC as well as your local time. And the reason for doing that is you can eliminate issues about what happens when the time goes backwards or forwards when it's daylight savings time. You might also include in there additional columns like engineering units. Maybe you have a raw value as well as an engineered value. You might have minimum, maximum, average type values. So there's a lot more things you can do using this sort of data log format. But this is a typical way of storing data, and this is pretty efficient from a database point of view, and it's pretty efficient regardless of whether you're storing the data or retrieving the data. So this is a good way of logging that data. Now, one alternative that we often see in HMI SCADAs is a group log. And in this case, what we have is multiple values per record. This is probably more efficient for data retrieval because, again, here, when you're retrieving data, you've now got a single timestamp, and against that timestamp, you have your 3 values. So for a trend or tabular report, this is arguably more efficient, although in practice, the database takes care of the efficiency. So I would say you're probably not that much different from where you were in the previous one. You could argue this takes a bit less memory space, and that may or may not be true depending on how the data is stored. One thing you need to think about with databases is it's very easy to look at this sort of format here and say, well, this is only using so many bytes. But what you don't know is you don't know what your underlying database is doing with regards to compression and any other sort of optimization of the data. So the actual data that might be used on your hard disk might be very different compared to the actual number of bytes we see just by looking at these on this sort of format. But this is another way of doing it. Again, quite efficient for data storage, potentially more efficient for data retrieval. Where this gets a bit more complicated is if you want to add additional columns. So we've got the ID, which is your unique ID. We've got your timestamp. But if you have to add UTC, well, that's okay. UTC is only one extra column. But now if you want to add any additional values for these point values you're logging, you've now got to add a lot of extra columns every time you do it. So if you wanted the raw value and the engineering unit, you go from 5 columns there to 8, because you've got to add another 3. If you wanted to add the engineering units, you've got another 3 again, so now you're at 11 and so on. So that's where this maybe gets a bit more complicated, is if you're storing a lot more metadata or other data besides just the point values. But I think these days, when people argue about what's the most efficient format between the group log or the data log that we just saw, I don't think there's much difference. And it really comes down to how much data have you got across the lists. So if you've got a lot of columns, potentially that could be more efficient. But with modern optimizations, you might find that logging with the data log that we saw previously is more efficient. So it's very hard these days to actually point to one or the other of these and say one is more efficient than the other. My preference would normally be for a data log, because that way you do have the option of adding in more metadata type columns very easily, where in a group log you maybe don't have that. But if you're only using the value for, say, trending, or maybe it's purely for a tabular report, then this makes more sense. So yeah, one of the questions you've got to ask yourself is, what the data is going to be used for initially, what might the data be used for in future? And this might be where a view or another query comes in to transfer the data or translate the table format from one to another. And you might even do that with a procedure or some other view maybe, or a query. So again, it depends how complex your application is as to which of these is best. And often there's no right or wrong answer. As I say, it's application dependent. So logging data is interesting because it's often time-based. You often want to log a value or set of values every second or every 5 seconds. Modern systems also let you log on change. You might only log when a value exceeds a certain deadband or a certain value. You might also have rate of change, so you're only logging a certain rate of change. Alarms and events though, these are different because alarms and events only occur when the alarm or the event is triggered. So it may be, for example, the start of a shift or the end of a shift. That could be an event. An alarm might be when a tank level goes too high or a temperature goes too high. So with these, you often have a slightly different table format, and we're no longer worried about the efficiency of storage. We are still we are still worried about the efficiency of retrieval, but the other aspect of logging alarms and events is we now often have a lot more metadata or alarm associated data. So in this case, you can see here we've got our timestamp on the left. We've got a sequence number, so that's like your unique identifier. Sequence number can also be useful to determine which order the alarms came in. And of course, you might have time stamping down to a millisecond, but if you haven't got that, the sequence number can also be a good way of determining which was the first up alarm, although that might not be reliable depending on exactly where your timestamp came from. So yeah, some systems, they let you log the timestamp from the device, if you're talking about a HMI SCADA, but often that timestamp comes from when you're logging in the database, or maybe it's for HMI SCADA timestamp. So that's another thing that needs careful handling, is how you handle that timestamp. Anyway, we've got the first two columns. We've now got the alarm ID. So in this case, it happens to be tank level. We've got an alarm class. So this is some metadata about the importance of the alarm. We've got a resource or plant area where the alarm came from. We've got what it was logged by. So in this case, this is a point database type logging process. If it was an event, it might be an event that's recorded by a user. For example, if you want to record set points, then you could log the username and the computer name where the data was actually modified. But in this case, it's actually being logged by a process that's running inside doing alarm capture. There might be additional references. Again, that could be the computer name or some other reference. And then with alarms, again, for 21 CFR 11 compliance, but also for reporting ease of use, you might want to log, what was the previous state? Was it normal before and has it moved to generated? Or was it generated before and now it's been acknowledged? For acknowledgement, yeah, that's another area where you might log who was the user who acknowledged the alarm. Was it reset or deleted or both? So yeah, in this case, we've also got columns to record what was the previous state, what is the log action we took, and what is the final state after the log action. The reason for doing that is it might have currently been in the generated state. A user might have acknowledged it, but at the same time then the combination of acknowledgement plus generation might result in a reset of the alarm, so the final state might be after reset rather than remaining in the generated state. So that depends on your system again. How are your alarms configured? What makes them go away? What is your alarm behavior? And then you've got that alarm message. So this is a human readable message. There might also be other codes as well, which are more computer level codes. And then we've got the generation time. So again, that's the reason you've got the two times there is you've got the timestamp when it was recorded in the database, which might be sometime after it was actually generated, depending on where your computers are. Are they all synchronized in terms of time? Are you generating this in a controller? Yeah, and there's a lot of aspects there around time. And again, you might need additional time formats for UTC versus your local time. But as a basic alarm and event log, yeah, this is a very good way of monitoring alarms, but you've got scope for a lot more columns there if you need it. What you could also do is potentially you could have a blended report where you correspond alarms with values. So you might be looking at different times, when, for example, the timestamp of the alarm was generated, what were some other values doing at that same time? So you might be doing that as part of your reporting structure. So again, having all of these different alarm columns with their different timestamps and so on, this allows you to increase the flexibility and complexity of your reporting to get more data about what actually happened if something failed or if you just need it for whatever purpose. So we've seen the concept of tables. Tables are the fundamental aspect of a database. Without a table, there's no data. Without data, it's not a database. Now, another aspect we get in is the concept of a transaction. A transaction is typically any single or combined query or update. So, for example, every time you add a new record, which is every time you log a new value or a new alarm, every time you delete some records, every time you transfer records between databases, if that's what you're doing, each of these is a transaction. It's a single query or update. Now, the reason transactions are important is really two reasons. One is we measure database performance in terms of transactions. And the other reason is we've got this concept of what we call atomicity or ACID. And this refers to a complete transaction that must run to completion in order for the transaction to occur. Now, imagine a bank transfer, for example. If you take money out of your bank, the transaction is that your computer system has to register that the money's been debited, and that has to inform your bank that the money's been debited, and it all has to happen. Otherwise, it could be that the bank system is debited, but you don't actually get the money. Imagine you're using a cash machine, the money doesn't come out. You need to be able to roll back that transaction so your account isn't debited. Particularly as well, if you're paying, say, from for example, from one bank to another bank, one bank must recognise that they've received the money, and the other bank must recognise that they've sent the money. Otherwise, you could end up with extra money or missing money. So, obviously, with money, it's very important. Generally, when we're talking about HMI SCADA or industrial automation, the concept of a transaction isn't quite so important, but you do get this concept of atomicity. So atomicity means it has to happen as a complete transaction. It's like an atom here. The idea is you can't split an atom. It's the smallest single component you can have. And ACID, that refers to atomicity, consistency, isolation, and durability. So ACID refers to the integrity of that database to make sure that whenever you do anything, the data is not compromised at all. Now, the other thing I mentioned there is database performance is measured in transactions per time unit. So there are benchmarks that you can achieve, and you can see how good a database is. So, for example, currently, if you look at something like Microsoft SQL Server, it has a benchmark of around about 2,000 transactions per second on a relatively powerful computer. So you could compare that against another computer system running the same database, or the same system running a different database, or a different system running a different database, and you could work out which one has the highest performance. Now, it's not always straightforward because transactions could be different according to what you're trying to do. But generally, having a look at a TPC performance benchmark, or transactions per whatever it is, that's a good way of understanding, is one particular database faster than another? And the reason we do this is, particularly in HMI SCADA and industrial automation applications, often we're logging lots of data. And that's another reason why a data log might be preferred over a group log or vice versa. When we do a group log, we can log multiple values as a single transaction, but when we use that data log we saw earlier, each data item is just one transaction. So potentially there's more efficiency if we go to using that group log, because we can have more data in the same transaction. These days it's not quite as simple as this. Transactions are a good way of working out which is the fastest database under ideal conditions, but your mileage will vary and it will depend on the application. And also now we have databases like InfluxDB, Timescale or Tiger Data, and those databases are much better at storing data at high speed and also allowing data to be retrieved at high speed, particularly if it's in a time series format. And we also have these historians as well. So for example, I mentioned SQL Server can store about 2,000 values per second if we count each value as an individual transaction. If you look at a typical historian, that can store 100,000 values per second. So it's 50 times faster. And also, it's not just about storing the data, it's about retrieving the data. So a transaction is retrieving or querying the data as well. So you might not be storing 100,000 values a second, but if you're using SQL Server and you're storing 2,000, you've got nothing left over to retrieve the data. So that means any reports you run would be very, very slow if they worked. Whereas if you put a historian with 100,000 transactions per second, then you could store 50,000 values and still read 50,000. So that's where these sorts of transactions per time unit, or the transactions sort of benchmarking, that's where it becomes important. There's another aspect to transactions, which is in a real database, and I say real, I talk about a relational database management system as opposed to a historian. The key point about transactions is they can be saved in a separate transaction log. So the benefit of doing that is when you back up your database, you could do a daily backup of the database itself, which could be really big. You might be talking about gigabytes of storage, which has to be stored on a tape. But rather than do that every day, what you might say is you'll store the database and the core files maybe once a week, but then you'll log all your transactions into a separate transaction log, and then you'll back up the transaction log, which will be significantly smaller. You might back that up on an hourly basis. So one of the reasons for storing transactions is it simplifies database recovery in case of a failure, and it reduces the amount of time that a backup might take to take place. So lots of reasons for using transactions. Very important in the relational database management system. They might be there even if you're not aware of them, but often what we find in these more historian type applications is we're not quite so concerned with transactions. It's more about just how fast can we log and how fast can we retrieve. But this idea of transactions is important, and if you do go more and more into databases, particularly for applications beyond automation and HMI SCADA, then this concept of a transaction is very important. One note on saving data into a separate transaction log. You do need to be careful there because you might need to prune that transaction log after time. An issue I found in some databases is you've got your original database and you've got the transaction log. The transaction log can grow and grow and grow. So you can end up finding, if you're not careful, you've got a lot of duplication of data there because you don't store all your transactions into the database. I mean, they should be there, but if you don't regularly prune or purge that transaction log or the old transaction logs, that can lead to disk storage problems. So there's another aspect of databases to be aware of. Again, you might not be aware the transactions are there, but they are. So you need to think about how are you going to handle that transaction log. So it's a good idea to have one, but you might want to have it purged every few hours or every few days, not just leave it to grow and grow and grow, otherwise you could run out of disk space. So once you've got your data into the database, which is done by the system, typically if you've got, say, a HMI SCADA, the HMI SCADA is responsible for logging the data into the database through the HMI SCADA configuration. So you can configure your I/O data, you can configure your tags or your points, you can configure your alarms or your events, and then the data is automatically stored into that database when the HMI SCADA is running. So the next thing you want to do is you want to query the database. Now, several reasons for querying the database. If you've got a HMI SCADA, then this often simplifies that database querying by using a trend tool, and by linking the trend tool to the database table, the trend tool will automatically bring back the columns that you select. So that makes it very straightforward to read the data and put it onto a graphical trend. So you can see what happened over the history of whatever your data logging time is. And the trend tool often has things in there. Some of them are more advanced than others, but typically there will be a start time and a stop time. But there might also be options for summarizing the data, minimum, maximum, average. There might be options for restricting the amount of data you read back from the database. So there might be interpolation as well. But often with HMI SCADA, the HMI SCADA makes it easy to query that database. Now, another way of querying the database, particularly for tables and reports more than for trends, is that you might require this structured query language query. So a bit of tautology there because we've got query twice, but this is where the SQL nomenclature comes from in the first place. So SQL stands for Structured Query Language. In the really old days, it was called SQL, which was a proprietary language, but then SQL was standardized by the American National Standards Institution, or ANSI, and then they renamed it as SQL. Some people argue that it was named SQL as a sort of way of spelling out SQL. Some people say that's purely random and actually it was just called SQL separately. That's probably lost in the mist of times these days, and different people you talk to who've got database experience might have their own view. But these days we talk about SQL, but many people who've been in the business for a long time will still call it SQL. And also SQL is arguably easier to say than SQL, so a lot of the newer people start calling it SQL as well. Now there are multiple flavors of SQL depending on which database you're using, and in theory they're all the same, but there are some minor and sometimes some major differences. So Microsoft has its own version of SQL called Transact SQL, or also known as TSQL. Or if you're using Microsoft SQL Server, then it's automatically assumed you're using Transact SQL and it's just called SQL. But it is different from other versions of SQL to do with the way the format works. Another interesting thing about Microsoft, Microsoft traditionally are not case sensitive. I've seen a lot of issues where database queries fail when people change the database because they haven't worried about the case. If you've come from a Linux or Unix background, then often those databases are case sensitive. So you need to be careful about the case. You might be spelling things correctly, but if you've got an uppercase character where the database is expecting a lowercase character or vice versa, then the transaction can fail. So you need to consult the database documentation for the specific syntax of the commands and also to understand if there are any other issues like case sensitive. Now SQL, you can often run that in your own query window. So for example, with SQL Server, you have the Microsoft Management Studio or the SQL Management Studio. That has an option to view the databases, view the database tables, look at all the relationships, and there's a SQL Query Analyzer in there. You can create and run SQL queries directly inside that Microsoft Management Studio for SQL Server. But you can also implement SQL inside programming languages. So often you might need to include a database library, and then what you do is create a SQL command, often as a string, and then you'll pass that string to the appropriate command. So for example, with VB or VB.NET, there's a SQL exec query command. So you'll create your SQL command, pass that SQL command to the SQL exec query function, and then that will return you some sort of structure or string, which is the result of the SQL exec query. I say structure or string, it might also be a number. If you're using a count type function, then the result might be a number. Again, that's something to be careful of because different implementations return the values in different ways. So you need to be careful how you bring back the data and how you handle it. So again, it may be case sensitive. You might get text data is surrounded by inverted commas or exclamation marks, or you might get numbers, but you might get the number represented as a string. So that's something you have to be very careful about is how you handle the actual structure in your programming language of, first of all, what is your SQL command going to look like, but then also how are you going to handle that return data. Anyway, SQL can be implemented either by itself inside your query tool, but it can also be implemented inside a programming language embedded into whatever your final application is. And also, if you're using things like reporting packages may have their own SQL query builders as well, which you can use inside the reporting package in order to build up the SQL query. So here is the first SQL command, and this is the most common. It's called select. Now I've got this in uppercase here. Again, your database mileage might vary, but for Microsoft, we normally put this in uppercase. And the purpose of the select command is used to retrieve data from the database. So a typical syntax is we have to say use the database name we want to select from, and that's not always required, but if you've got multiple databases, then your system may require that. You then have to say the select command itself, and then you either say the specific list of column names you want to select from, because that can be a subset of your overall table, or you might say select asterisk or star, which would mean every single column that's in that table. You then say from, so you're saying select star from and then your table name, and then you've got some options. So you might order by ascending or descending, depending what you're reading. and you might have to specify which column you're ordering on. And then you might have a where clause. A where clause is really useful because what you do there is you specify a column name and a set of values that you want to retrieve. So like we saw earlier, we've got that group log or the data log where we're logging multiple values, multiple tags. If you just wanted to bring back data for a certain time, you might use a where clause on the timestamp. Or if you just want to bring back certain values in the data log, you might just say where the point ID or the tag ID equals tag .1 or whatever the tag name was. Equally, if it was a group log, you might specify the column name where you want to bring the data, and you could restrict it that way as well. And there's a variety of different variations on this. You can also select distinct to only return unique records. That ignores duplicates. If you want to count the number of records in a table, you can use count. One good thing is, depending on what your implementation is, you might want to do a count first to work out how many values there are. For example, so if you're using VB.NET with that SQL exec query, if you read all the data, you might find it overwhelms your VB.NET implementation and you can't read all the data because the return query is too big. So you might want to do a count first to make sure that the amount of data you're going to return is within a certain range. Another reason for doing a select count is you might actually want to make sure you do bring back some data at all. Yeah. Otherwise, you might be doing a lot of calculations on an empty field that's been returned, and that can cause runtime errors. If you're trying to do something where there's no data, then you could end up with a divide by zero error, or you might just end up with null string errors. So you might want to do a select count first, just to make sure you actually are bringing some data back. And you could also do a select count just to make sure there's only one item of data as well, so you're not trying to work on a table that's bigger than you expected. So lots of reasons why you might use those variations. And there's some more syntax we can use on select as well. There's things like joins and so on, but they're a bit more complicated. So you can use that select command to bring that data from multiple tables and join all the data together so that you can have a single result based on data coming from multiple tables and even from multiple databases as well. But at its simplest format, you select the column names you want to use, you specify the table name you want to bring them back from, you typically put a where clause in because that's always useful, and then just to make sure you might use an order by command as well, typically ordering by date or time, just to make sure that everything's coming back in the useful order. So how do we select data from more than one table? So as I mentioned, you can select to retrieve data from more than one table. You can select star from multiple tables, in which case it returns all of the tables in table 1 and table 2 in this example. You can also specify particular columns from one table versus another. And again, then you can also choose that where criteria, and you've got a variety of different criteria depending what database you're using in. So the where could be equals, less than, greater than. You can use binary operators like and, or. You can also use in, or between, or like. So depending how good your database is, you've often got a lot of flexibility here in terms of your where clause to bring back your data. You have to be careful how you handle strings. With Microsoft SQL Server, you have to handle strings inside single quotes, but that might be different for other databases. And you can also use wildcards. So you might say a where criteria where a column name equals asterisk. But if you're going to do that, of course, it's just going to bring back everything because your wildcard is everything. But wildcards can be useful, particularly things like % to replace individual characters. But more likely you're going to be selecting against a known value, or you might be selecting against, say, a start time and an end time. So you might need several where criteria. So you might say where date time is less than 1 and is greater than and equal to another. So you might be having a combination of criteria there in your where clause. But that's a pretty simple way of bringing back data from several tables. But again, be careful not to bring back too much data, and also be careful how the data's mixed. Because if you just do a raw select like this, you could end up with multiple mixed columns that might not work together. This could also be a problem if you've got more data in one table than another. Your data format might end up being unexpected compared to what you were thinking you were going to bring back. So you do have to design your select clause quite carefully, particularly in larger and more complicated databases. And they can get more complicated. You can nest select commands. So you might say, let's bring back some data from one table, and then you might want to do a different select on top of that for a different reason. So you might want to do select star from a particular table where there's a criteria, and then you might want to select the count from that. You could probably do the count more easily than that, but yeah, that's probably a bit of a tautological example where you don't need to do it this way. But certainly there might be reasons where you want to do a nested select. You can also, as I mentioned, use join, and there's also union. So these are ways of doing a join on two different tables to only select matching values that are in both tables. So that's where a join would come in, and you can do an inner join or an outer join. And this gets quite interesting now, because this also extends into set theory, and this is where databases originally designed. It was all about having a set of data, and then you'd have another set of data. And the idea of doing a join is, if you had those two sets were overlapping, the join is effectively where are you overlapping, what's in that middle bit, and that can define where you do your selection. So in inner join, you would only select the data where you are overlapping. An outer join would be all of the data that's outside of that inner selection and everything else. So there are multiple join types depending on what data you want to bring back from which table and how you want that table to be sorted. So you've also got the option of using a union there. Yeah, that combines the result set of two or more select commands. So again, a similar way of joining two tables rather than having just multiple selects or a single select. So lots of things you can use there, and I won't go into these too much. These normally aren't used for simple databases, particularly in HMI SCADA applications, but they probably would be used if you're doing something more complicated. So for example, in the past, I have created a maintenance management system based on HMI SCADA. The HMI SCADA was the front end, and that was running scripts on the SQL queries in the background. And you could make that quite simple by simplifying your table structure. But as soon as you get into the database purism and you start trying to normalize your tables and make them more efficient, that's when you need to think about these union and join type commands to make sure you're bringing back the right data. And the reason you're doing that is you don't put all the data in a single table. Like I say, you would maybe have the tag name. The tag name would then link to another table, and that other table would have your descriptions in. And the reason for doing that is to minimize the space that the database takes. Otherwise, you might have to store a long tag name description every time you've got that tag name, and that could be very inefficient. So let's look at some other SQL commands. Here's one called create, which surprisingly is used to create a database or create the table or both. So what you can do is, with the create table name command, you use create table, you specify your table name, and then inside brackets you have your column 1 with its data type, your column 2 with its data type, and so on. And in this example, that will create a table called table name with 3 columns of your specified data type. So if we go back earlier, you have that data type. One might be a timestamp, like time or date. We might have the string for your tag name or your point name, and then we might have int to store your point value. So again, you have to refer back to your documentation of your database to work out what those data types are. When you've created a database, there's a corresponding drop command which can be used to delete a database or delete a table. Now the create command, if you're using a HMI SCADA, often you'll never need to use that create command yourself, because the database will automatically create the database table when it runs. So that's rarely required. But once you come outside of the HMI SCADA type environment, then you may well end up using create commands. And you often use this initially once to create your table, and then probably never again. Yeah, unless your database is deleted and you have to recreate it, or maybe if you're deploying an application on multiple different locations where you need a new database each time. But in a lot of applications, you either don't need this or you run it once and that's it. A lot of tools as well, so particularly if you're looking at, say, the SQL Server Management Studio, that does let you create manually as well. You don't have to create using this tool, using a create command. There is like a what you see is what you get type tool, a bit like building up a spreadsheet. You can say, I want to create a column, this will be its data type, then you'll add new and you'll create another column and so on. And then also then there are other options on the create command to create things like keys, unique values, automatically incrementing identifiers and so on. So depending what database you use, there might be additional aspects to the create command to specify what you can have in there. And also that covers rules, that data type, but there might be additional restrictions to say you might have an int, but it might have a minimum value of 0 and a maximum value of 100. And if your data exceeds those values, then the database won't let you insert that because you've broken the rule for that table. So there are often a lot more aspects to creating the database than just the ones I've mentioned here. To insert into a database, we use the insert command. This is used to add data to a table. Conceptually, data is added at the end of a table, but this is something that you don't really know what the database is doing. You don't know what the actual internal format is. The database management engine hides this from you. So actually, the data could be going anywhere and in any format. You don't really know. But conceptually, data is added at the end of a table whenever you use an insert command. So to add data, you use insert into, you specify the table name, then you specify the column names, and then you specify the data for each column. And this is pretty much the Transact SQL format for this. So the columns are followed by the data names. Now, if you go back to the previous slide, you'll remember that when we do the create command, these are in different formats. Why is that? We don't really know. These are maybe lost in the mist of times. There's maybe some people out there who might have an opinion or maybe even a real reason as to why these commands are in different formats. But these are what we live with because this is the standardized SQL language. It's not necessarily fully consistent, but that's okay. It's what it is and it's how it works. But this is the insert command. Again, if you're using a typical application like HMI SCADA, the HMI SCADA automatically performs the insert commands whenever it adds a database value like a tag name or a tag number or a value or an alarm or event. Those are automatically run. But if you're doing your scripting or if you're writing your own application, then you may well end up using the insert command yourself. Insert is often run more often than any other command because although you as a user might be using select to query the data, the insert command is the one that's actually inserting the data first of all. So particularly if you've got a database that's being regularly updated, the insert is possibly the most common one that's run. Again, behind the scenes, we imagine that the data is inserting at the end of the table, but in practice, we don't really know that. We don't know what the format of the database is inside. So it's up to the relational database management system to optimize its own data management and its disk usage and its CPU usage. And the RDBMS will handle what the actual data looks like inside the database table itself. But when you do your select, again, the RDBMS reverses that and you get meaningful data. So another command we have is update. Update is used to update or change an existing record that matches a specified criteria using a carefully constructed where clause. And why do I say that? Well, the reason is if you don't carefully construct your where clause, it's very easy to end up updating or changing the wrong record. And if your where clause is particularly badly constructed, you could end up updating everything in the database. So you've got to be very careful how you use this. So I would try and make sure your where clause is narrowed down to an individual data value or maybe a slightly bigger set of data values, but you really want to be very careful. Otherwise you can end up updating everything and that can, of course, that can destroy your data integrity. The data might still be okay from a database point of view, but it might be useless from an actual retrieval point of view. So you've got to be very careful where you use an update. So you say update table name, set, and then you specify the column 1 and the data you want it to be, the column 2 and the data you want it to be, and so on, followed by your where clause. And then again, that's got to be very carefully constructed to avoid updating more data than you want to. Again, the format of the structure, the actual SQL command has changed, but that's how SQL works. This is the way it works. Again, where can include equals, greater than, less than, and or, in between, like, etc. And what I recommend is if you're testing a system, before using the update command, I'd recommend using a select first to make sure that you retrieve the correct record you want to update, and then you run the update command afterwards. But this could be quite useful on a global basis as well. Maybe you change a tag name, so you want to update everything that's in your database. So in that case, you might just say update everything where that tag name equals the old name, and you would update it to the new tag name. So there are occasions where you do want to modify a lot of data, but equally there might be occasions where you only want to modify a single record. So you do have to be very careful how you use this command. So I think we talk about backups later. Again, if you do get it wrong and corrupt your database, then you have to restore your backup. That's how you get back. Sometimes though there are undo commands, but often once you run one of these commands, I mean, select is okay because you're not modifying the database. Create, well, you're probably just creating the database. You could always drop it and recreate it if you got that wrong. Insert, that's only inserting a single record, so you're not too worried about that maybe. But update is something that can have a wide effect across your entire database. And often, an update, once it's committed, everything is updated. It can be very difficult to undo. For example, you might have two different tag names, and you need those two different tag names for a reason. If you accidentally update one of those tag names to match the other tag name, you've now lost the integrity of the data, because now everything has the same tag name. So you've now got no easy way of going backwards because you haven't got that independent thing as you had before. So another option on the update is create an additional column inside your table and update that column, then check the new column is correct, and then maybe delete the old column afterwards, because otherwise you've got nothing to go back to. So that's another way maybe of making sure that you're not making mistakes, is update into a new column rather than update an existing column. Now, you don't always want to delete data from a table, but it is possible to do that. For example, in HMI SCADA terms, you might want to delete any data that's too old. So if you've got a 30-day event log, then once you get to 31 days, you want to delete anything that's 31 days and older. So there are occasions where you might want to delete data. So we do have a delete command. This is different from drop. Drop deletes an entire database or an entire table. Delete is used to delete data from within a table. So don't get those mixed up. Although some databases do let you mix and match, so you'd have to consult your database documentation to understand which to do. But generally, in the proper formalized SQL, delete is very different from drop. So what you say is you say delete from, specify your table name, and again, you need to carefully construct that where clause to make sure you're deleting the right data. So you might say delete from data log where timestamp is older than 31 days, for example. That one's pretty clear, but you do need to be a bit careful, otherwise you might end up deleting a lot more data. So again, you can use that select first to test that the where is correct before you actually run the delete command. And then again, with the where clause, you've got all of this criteria, including wildcards. So there are some things to be aware of with databases. One thing is a concept of null. Now, some people think that if they've got a value of 0 in a database or an empty string, that means no data. Well, with a database, you've got this additional concept of null, which is empty or unassigned. And this is different from 0, and it's different from an empty string. You've actually got this concept of an empty data value or an unassigned data value. Not every database supports this, but the idea here is that when you insert data into your database, if your table structure lets you, then if you haven't got data for that particular item, then you can end up with a null field. Like the example I used earlier. So when we're logging an alarm, for example, if the alarm was called by an operator, you might want to log the operator's name, but if the operator name doesn't exist, you could leave that field as null or empty. So you can then do queries inside your database, and you can actually search for if null or if not if null, and you can use that in queries, and that can be a useful way of retrieving the data in an additional way. May not be that important for a typical HMI SCADA application, so you may just populate that with 0 or an empty string. And again, your HMI SCADA may have different operational methods depending on how it's constructed. But certainly in a real database application, you may come across null, and null does have its own implementation. One thing, for example, you might have a null area where you haven't assigned a value yet because it's going to be calculated later. And then later the value might actually be 0 or an empty string if the calculation had no output. But yeah, then you can actually differentiate between there is actually a result from the calculation versus null, which means the calculation hasn't been performed yet. So null does have its uses. However, you do need to be a bit careful. Yeah, if you bring data back from a database into something like vb.net, then you're comparing a null string might be hard work. So that's where if null or not if null come in, because if you try and compare null with a 0 or an empty string, yeah, you might get some sort of data exception error which could cause problems. So null causes problems as well as giving you additional capabilities. Now, another thing to be aware of is that data types matter. Yeah, the number 0 is not the same as a string value of 0. Some databases will let you directly compare the two, but often if you've got a number column, say an int column with a value of 0 in there, and you compare that with a string value which is 0, they're both 0, and if you looked at it yourself, you would see they were both 0 and you'd think they're the same. But the database may well decide that the number 0 and the string value 0 are not the same. And the reason is one is a number and one is a string. So they are definitely different. So you might have to use conversion functions in queries to be sure. Not all data types can be converted. You can convert a number to a string quite easily, but you can't necessarily convert a string to a number if the string isn't a numeric value. So conversion functions, that includes things like cint to convert to integer, cfloat or creal. So there are those conversion functions, but just be careful, because if you run one of those functions on a data item that can't be converted, then that could give you a runtime error. Another thing to be aware of is true and false. False often equals 0, which is fine, but true may be 1, but it can be -1. So yeah, be careful when you're converting from one format to another or comparing values between databases. You might say that, you might try and do if true equals 1, and that would fail because in the one language, yes, true is 1, but in the other language, true is -1 and they're not the same. So that's another thing to be careful of. Let's move on to a different topic. I've talked about keys, and there are two aspects here. There's what we have is a primary key and a foreign key. And I just want to formalize what those mean, because I might have got them mixed up earlier. But what you should typically do in every table, there should be one column which is assigned as the primary key. Now, if you've got simple data and you're not worried about comparing data or mixing it with other tables, then maybe this isn't required. But in a normalized database, this is a best practice, is to have one column as the primary key. So each entry in that column must be unique. It is not allowed to be null, but it can be assigned automatically. So for example, in SQL Server, you can have a concept of like a seed value, which can start at 1 and then be incremented by 1 each time you use it. So you get 1 in the first value, in the first record, 2 in the second record, and so on. So you can have it automatically assigned. It might also be your primary key is already unique for another reason. So maybe if you're logging a timestamp, if your timestamp is based on the UTC time, then if you're not logging more than one thing every second or every millisecond or whatever your particular resolution of your timestamp is, then that could be the primary key, although that can be harder to handle. You need to be careful there, of course, though, because if you're using local time, if the clock goes back at the end of the year, you might end up with a duplicate primary key, and your database won't like that. It will often kick out the new value because primary keys have to be unique. Now, the reason for using a primary key is that what we can do is we can have a primary key in one table, and that can link to a value in another table, and in the other table it's known as a foreign key. So for example, if you had your database like we discussed earlier, where you have your tag name, and then you have another database or another table where you have your tag descriptions, what you could use is you could use the primary key inside your descriptions field, and that could be linked as a foreign key into your table that's got all of your tag names in it, and that way you could use that to avoid having multiple tables or avoid having additional data by using multiple tables, and then that allows for normalization as well, and then that improves the efficiency of your database, particularly with regards to database storage. So this needs some clever design of your database, but it's a good way of having a large database and by linking all of your values together. Another example is, let's say you've got a CRM system. You might have an account called Acme Limited. If you have a contact for Acme and then that contact has an address, if you're not using multiple tables, then every single record for Acme has to have the address duplicated for every contact that works at the Acme organization. So that means it's inefficient from a storage point of view because you've got to store the address multiple times. It's also very inefficient if you have to update the address, because if you've got 100 contacts at Acme Inc. and you update the address, you've now got to update it 100 times for 100 different contacts. Much better to have a other table which has the address in, so you'd have Acme with the contact, and then you'd have the foreign key which points to the primary key in your addresses table, and then you only need to store the address once, and it's much easier to find and update the address. So that's why we do things like database normalization, and that's why we have multiple tables. It's about rationalizing the amount of storage we use, still making the data easy to retrieve, but also the database itself, the RDBMS. The RDBMS is very good at optimizing it to make sure that that is the most efficient way when we store the data and when we retrieve the data. Now, I mentioned normalization. Normalization is a process of subdividing the database to reduce the amount of redundant storage. Typically, you go through 3 stages of normalization. I would say in data logging applications with HMI SCADA and industrial automation, it's rarely used because you're more concerned with performance than disk utilization. But once you get into a large CRM or SAP like ERP system or whatever, then normalization becomes a lot more important because it's about efficient use of that data and an efficient storage of that data on your disk or disks. So normalization is something that we do have to consider, particularly in large database applications, but you might not come across it if you're just doing a HMI SCADA type application. So here's that example I mentioned earlier. If we've got a non-normalized database, you can have one table with redundant data. So here we've got 3 contacts, all working for the same company. They've all got to have a record inside for the company address, and you might have the address 1, address 2, the city, the phone number, the website. So those last 5 columns consist of duplicated data. So what we would do is we would normalize that data, and the way this works is we have a table for the contacts, which on the left hand side there, and then we have a table for the actual address. And I'm just looking there, that's not quite right because we're missing the company name, but never mind. This is an example of how you could do it, but there's a bit of data missing. Anyway, in the company address name, you would have one record for each of your different addresses, and you would have the primary key there as the ID column. For your contacts, you've still got the primary key, which is the ID, so 1, 2, 3 on the left, but now you've got your foreign key there, that's the one that links to your primary key in the address column. So we've actually missed out a column because we haven't got the company name in there, but we have got the address. But this shows how the normalization works. And what this would happen is, this would reduce the amount of disk space that's used, but also it can improve the performance, because when you're retrieving the data, the database management engine uses that foreign key address to the primary key address, and it uses that to optimize the retrieval of data. Now, this can be counterintuitive, but one of the things you need to think about is when you're managing data, the CPU is often a lot faster than the disk. So if you've got your data stored in 3 different places, you have to go to the disk 3 different times to bring that data back. So because you're waiting for the disk more than you're doing the processing, this is actually more efficient to do it in the normalized way, because you've only got to go and read the data off the disk once, and the next time you're handling it, it's already in memory and the system can optimize performance that way. So again, this is something that may not always be obvious. You might think that it would be quicker to retrieve on the first one because you don't have to do this multiple linking of tables, but because of the delay it takes to actually read data off the disk, it's actually faster to do it the second way. Same when you write data. There's a bit more work required because the system has to look and see, does that company ID already exist and do I have to create a new one? But again, often that's an internal calculation using memory and CPU cycles, which is a lot faster than writing multiple values to the disk. So there might be some trade-offs about whether it's better for retrieval or storage and so on. Again, with HMI SCADA applications, we often don't care because it's more about efficiency of the application and not making it too complex. But in a large application, it is actually more efficient and also faster from a CPU cycles point of view to do it the second way. Now, we mentioned indexes earlier. The idea of an index is that you put an index on the table to improve retrieval performance. So what happens is, rather than look through the table, the system uses the index for retrieval. And the reason we can do that is that we can sort the index very easily, whereas sorting the actual underlying table may be difficult or time consuming. Again, you've got to think about CPU cycles, but there's also reading and writing the disk. Now with modern SSDs, they're fast, much faster than old rotating hard disks, but even with a fast SSD, you've still got the concept of having to read and write to the disk, and doing it in memory in RAM is a lot faster than doing it on the disk itself. Now, having an index, what you do is you have to specify to the system how many indexes you want, but if you have too many indexes, that ends up reducing performance. If you're never retrieving data, if you're never inserting data, then it doesn't really matter. An index is always going to improve performance. But when you're writing data, remember that every time there's an index, you have to recreate or resort that index when you insert. So if you've got too many indexes, so for example, let's say you've got a table which has got 4 columns. If you index on every single column, each of those 4 indexes has to be resorted every time you insert, in which case it might be quicker just to resort the entire table by itself. So too many indexes can reduce performance, but what you do is, if you create an index on commonly searched columns, then that can significantly improve performance. So indexing used to improve retrieval performance, and I've seen applications where reporting times have been reduced by 90% just by creating an index on a table. Or equally, I've also seen applications where there's been too much indexing, and removing an index can improve write performance quite significantly as well, particularly if it's an index that you're not using very often. So often this is application dependent. You need to look at the application, you need to look at the types of reports people run, you need to look at how frequently those reports are run, and it may be you have to say, well, we're not going to index this one. If we ever need to do a report on that column, we just have to accept it's going to be slow, because the alternative is every time I write to that table, we're affecting the write performance. So it's always a bit of an engineering trade-off and a performance trade-off. And that may change over time depending on the types of reports you do and the amount of data you insert. But certainly it's recommended to create an index on any commonly used column where there will be some sort of search activity. Now, if you've got a very simple application and it's all on your local disk, security doesn't really matter because you're the owner of the database, it's your database, you've got full access, you're maybe the only person there. If it's a HMI SCADA application, then the only way you can get to the database is through the HMI SCADA itself. So security isn't really a problem on very small and local applications. But as soon as you start scaling those applications up, you need to think very carefully about database security. So typically we start with an administrator for the database, and that's called a sysadmin or an admin. Now, although the sysadmin is in charge of the administration of the database, they don't necessarily have access to view the data. They might have access to view what the columns are, and they might have access to view what the indexes are, and they might have access to create indexes and add columns, maybe even delete columns, maybe add tables and so on. But it might be for that admin, you don't necessarily want them to be able to view what's in that database, particularly if the data is very sensitive. So the sysadmin is responsible for the administration of the database, but not necessarily being able to view any or even all of the data. You then assign users. So the admin and the sysadmin might be different from the security admin, although they might be the same person, but another admin or the same admin will be responsible for creating users and assigning access to the actual database itself. So depending which sort of database you get, there can be a very fine level of granularity. You might define access at the database table level. So it could be a user can be read only for a particular table, or maybe write only, or maybe read and write. But what you can also do is you could say, well, I only want that user to view particular columns in that table. So this is where views come in. So you might say this user cannot view that table, but you would create a view which is a restricted set of columns from that table, and that view would restrict what data is allowed to be viewed by that particular user. You could also maybe have a more complicated view, and you could maybe even do a select with a where clause, and they might only be able to view certain values from that table. For example, if you've got a CRM, you might split by regions. You might have, say, a salesperson who works in the north of a region. They would only be able to view customers from the north. And then you'd have a corresponding sales user for the south of the region who could only view users from the south. So you would give each of those a view, and then based on that view, that would restrict what they can. And of course, you'd need a column somewhere with a value of north or south, and your view would have to take that into account. There's also other database configuration capabilities which users might be assigned to. So you might have a backup or a delete admin. You might have another sort of user who can only create databases but can't delete them. So the idea is you can get lots of different user types with lots of different capabilities, and it might be there's no single person who has full access to the entire database. So that database security, it does need a lot of planning. One thing to help you with the planning, if you've got lots of users with similar privileges, you can assign those into groups. So you might have more than one salesperson in the north, so you would assign them to a group called north, and then you would give them the similar views, and that would mean anyone who works in the north would be able to do that. Now, if you've got Microsoft SQL database security can be synchronized with a domain or Active Directory, and that can simplify administration. So in large applications, it's not just about the database security, it also links into the whole operating system security and whatever else is capable for that person to be able to do. So this database security, this isn't necessarily a trivial thing. In a big database, this can be a role for one or even multiple people on a full-time basis, just to decide who can and can't see what data, and also who can and can't see or who can and can't see or do particular functions on that data. For example, you might have users who can view data but can't modify it. You might have users who can modify data but can't delete it. So that, again, multiple levels of access, which is all part of your database design. Not an issue for small applications, but certainly a big application for large systems like CRMs, ERPs, and so on. So I touched on database performance earlier when we talked about transactions. Now, a lot of people will say, how fast is this database? And ultimately, although we can do performance benchmarks, those benchmarks are just benchmarks. They'll work fine on a bench, but as soon as you move your computer to a different bench, they may change, because you're running a different type of database, or maybe your computer has changed. Maybe you've got a computer with more memory or a faster CPU or a faster disk. So it's a bit like asking how long is a piece of string. There's only one real way to measure database performance, and that's to measure it on your application And even then that might vary from day to day depending what else the computer's doing. So Microsoft and Oracle, they are recognized as pretty much the fastest transactional type databases today, handling about 2,000 transactions per second. Can be a bit faster if you've got a very powerful computer, but think about very large applications. What they often do is they often have distributed databases. So you might have a database engine with multiple distributed databases. Each database is handling about 2,000 transactions per second, but then it's all about how many database engines and how they're synchronized and so on. So so that's for very large applications. I'm thinking here like imagine YouTube where people are uploading videos, or imagine Amazon where people are buying items and there's probably millions of people hitting that buy button every minute. So they're going way over that 2,000 transactions per second, but those are very specialized systems. So when we talk about 2,000 transactions a second, we're typically talking about a single database instance running on a single computer. And that's going to be quite a powerful computer. It's going to be a multiple CPUs, because the more cores you've got, you can distribute your processes across those cores, and the modern relational database management system will do that. You need lots of RAM, because if you want your systems to run optimally, you'll be loading them in memory, not running them on disks. But when you do read or write to disk, then you need fast disks. So that 2,000 transactions per second, as I recall, that's something like a 16-core CPU with 32 gigabytes of RAM and high-speed SSDs. And when you benchmark, of course, that's running it against a particular benchmark sequence. So what you get in the real world may well be different depending how powerful your computer is, how much RAM you've got, how many CPUs, how many cores, how fast your disks are. Another thing that can vary is what does your transaction consist of? Transactions can consist of writing more than one record. So there is a possibility of doing a bulk transfer. This is something that SQL Server lets you do to speed up your writing performance. What happens is the database sort of assembles several queries together and then, or several transactions together, and then it loads all of those transactions onto the disk in one go to improve disk performance. But you've got to remember as well, performance includes reads and writes. If the writes are at a maximum, then reads can be very slow. I've seen this before with HMI SCADA applications, logging to Microsoft, logging 1,000 values per second, and there was no overhead left over to actually read anything. So a report was taking about 8 hours. So this is where time series databases come in. They are optimized to allow much higher performance read and writes, provided that your data is stored on a time basis. So they're no good for event type data, although they can be, but really they are optimized to store data where it's coming in on a time basis. So every second, every millisecond or whatever. So typically we find with a time series database, they can easily allow up to 100,000 data items, reads and writes. So now, if you're storing 2,000 items per second, your reports can be very fast because you can read 98,000 per second. You haven't got to worry about your 2,000 transaction limit being exhausted. But remember, these are often customized databases. They do have higher performance, but they are optimized for data with a timestamp and not necessarily on a transaction basis. So you might not have a transaction log. You might have different ways of storing the data. You might have to use different types of querying information. You might even have to buy a different database. So typical historians, there's OSIPy, there's gHistorian, there's AspenTex IP21. So although they offer very high performance, they also come at a price because they are special optimized databases specifically for this time series data. More recently, InfluxDB is an open source database that can do time series data. And you've also got that Tiger data, which is an option for Postgres, which optimizes Postgres to handle time series data. So it can be quite complicated in terms of how they're managed and how you install, and they can also be quite expensive. But that's roughly what you can expect from a database. If you've got a typical SQL database, 2,000 transactions per second read and write, although it can be more complicated than that. And a typical historian or time series database, 100,000 data items read and write. So what are the practical implications for that? Well, if you've got 2,000 transactions per second, for many commercial applications, that would be fine. Imagine you're running a CRM. How many new customers do you get? How many orders are being placed? How many opportunities are there? How many times are you updating contacts? So let's say you're an organization that's got 1,000 employees, you've maybe got 1 million customers. Yeah, if you've got 2,000 transactions, but you've only got 1,000 employees, it's unlikely that every single employee is going to be doing 2 transactions per second. So you're fine for writing. So more likely with that number of employees, you've probably only got at the most 10 or 20 transactions per second writing the values, which means you've got quite a lot left over for doing reports. And often in the commercial organisation like that, you'll report it. It doesn't matter if it takes a few seconds or even minutes to run. Ideally, you want it to be fast, but some systems, what you do is you hit the report button, and then it sends the report to your email address a few minutes later. So you don't care, but it takes a few minutes to generate a report, as long as the data's correct. Industrial applications, though, may need much faster performance. Remember that jet engine I talked about earlier, the gas turbine, which is being used for power generation. It might be running at 3,000 RPM, so that's 3,000 revolutions per second. Maybe it's got 20 gas injectors. Maybe you're measuring the temperature at 20 different points. So now you've got something like, 60,000, but that maths may be wrong, but you've maybe got 60,000 values you want to write every second. So, that's a much faster industrial application. And maybe you've got more than one gas turbine. Often they're in pairs, so you can run one while the other is down for maintenance and so on. So now you've potentially got 120,000 values per second. So that's where your historian comes in. So there's a few things you can do. You can use SSDs, much faster than standard hard disks. One thing you have to be careful of SSDs though is they are really good for high-speed read performance, but they're not very good for high-speed write performance, because every time you write to an SSD, you start to wear out the cells. And what happens is with a typical modern SSD, you can write to each cell about 2,000 to 3,000 times, and then that cell is either then no longer used or it becomes read-only. So what happens there is if you're writing lots of data to your disk, if you're say writing 100,000 values per second, you could be writing several gigabytes of data per day. And even if you've got a very large SSD, you could overwrite it within a matter of a few days or weeks. But the answer is, modern SSDs, you can fit larger SSDs, which is called over provisioning. Some SSDs use write buffers, so you're writing to RAM rather than the actual SSD itself, although ultimately you've still got to write to the actual SSD. A lot of modern SSDs support wear leveling. So you might have an individual cell that wears out, but with a combination of wear leveling and over provisioning, the SSD can actually handle a lot more than those 2,000 or 3,000 writes before it becomes read-only. There's also a possibility to get enterprise level SSDs as well. But I definitely recommend SSDs. Even if you know you're going to be writing a lot of data, just make sure you get a very large SSD. Over provision it by 4 to 10 times. Yes, you'll pay a bit more for the SSD, but by over provisioning it, by having a lot more memory than you think you'll need, it will last a lot longer than if you just try to use a much smaller SSD. SSDs are much, much faster, and also, particularly industrial applications, you don't have issues about shock or vibration. If you've got a mechanical rotating hard disk, shock and vibration kill the disk. And also, with modern, with these rotating hard disks, the bearings wear out. A good enterprise level hard disk that's spinning 24/7 might wear out after 5 years. What can happen then is you turn it off, you've got a Christmas shutdown, it goes off before Christmas, you come back after New Year, you turn it on, the bearing no longer works, the disk does not spin, and the disk is ruined. So with SSDs, of course, no moving parts, so you don't have to worry about shock or vibration, you don't have to worry about bearings, but you do have to worry about that potentially disk wear because of the number of writes. But again, modern SSDs also overcome that. You also need to think about scalability. It's all very well saying that 2,000 transactions is fine. we often get people in industrial applications starting off with SQL Server because they think it's only small, 2,000 transactions, I'm writing 1,000 values per second, I'm reading 1,000 values per second, no problem. But in future, the application grows and then your choice of initial database becomes a problem. So you end up having to migrate to a different database. So ideally, if you knew your application was going to grow, you would start off with that high performance time series database from day one. You wouldn't be messing around with a smaller database to begin with. However, there are cost implications, of course. So sometimes you just have to accept that sometime in the future, if your application does grow, you're going to need to somehow migrate all your data from the old database to the new database. So here's a few more practical implications for database performance. One thing, we mentioned some of these, if you can index commonly searched where columns, that can improve performance. But just be careful, because if you add too many indexes, then you do add load to the database server, particularly when you're writing. So just be careful of what you're going to index. But adding some indexes is normally a good solution to slow performance. But equally, sometimes removing indexes can also help, particularly if you've got a lot of indexes. Check to see where the indexes are being used. You want an index where you commonly search or sort, but you don't want indexes where you're not commonly doing that. Now, I mentioned about normalization of data. This is something I've seen where database purists come in and they say, we've got to have completely normalized data. We want no duplication of data whatsoever. But what happens there is, particularly in high-speed data logging applications, if you've got too much normalized data, it can reduce insert performance. So sometimes denormalizing your data and having redundant data, yes, you're using more hard disk space, but that's okay because it can improve your insert performance. So for example, normally you would want to limit the number of database or disk writes. So you do need to be careful how you do your denormalization, because sometimes normalizing your data actually reduces the disk writes, like the example earlier for the address. If you've already got the address stored, you don't need to write it again, you just need to write that foreign key. But sometimes if you've got a lot of different values you're doing, for example, alarm messages, each alarm message is unique, trying to normalize alarm messages can be very hard. It's actually better to accept that you're going to have some denormalized alarm messages there and just log each alarm message individually, even though it's going to be some duplication perhaps, and it's going to take up more disk space. Another thing is, don't have too many unique keys. You can use this unique property to ensure that new data does not already exist. But as soon as you do that, the system has to check to see if that data already exists. So effectively it has to do a select before it can do the update or the insert. So I would say there, don't have too many unique keys. So again, this might lead to duplicated data, but that's okay, because sometimes that insert performance is more important than the actual data itself. Another reason for having those unique keys is for data integrity, but you can always resolve that at the select stage using a distinct clause, or by doing some other sort of criteria when you do your select command. Now your database may vary, so check to see what is the memory utilization, what sort of buffers you can configure, what sort of data types are there. Data types, again, that's interesting because a lot of people store the data as a float, but maybe you're just storing integer data. If you store it as a float, first of all, you're probably using 4 or 8 bytes when you could be using 2, but also you've got that issue of not just more memory, but you're writing more values to the disk, which slows it down, and there's more handling inside the memory. So consider your data types. Store data as integer rather than as a float. Maybe look at your length of your strings. If you're storing an alarm message, maybe you can compact that alarm message and limit your alarm messages to say 32 bytes or 32 characters rather than say 128. Again, it will optimize the disk storage, and it will also optimize that write performance. The database itself, some databases let you configure how much RAM you use. You need enough RAM for the remainder of the system, but you also want to enable the database to use RAM as well. So for example, if you're using SQL Server, you can actually configure how much memory it uses, and you want to offset and optimize how much memory is the database using versus whatever else is on that computer. And you can also configure buffers. Longer buffers can help, because what can happen is you can have a buffer where you fill the buffer during a period of high speed writes, and then the buffer empties slowly, and that can help you overcome surges of data. It's no good for sustained data writes, because the buffer will just be filling up and then get too full. But where you might have surges of data, for example an alarm flood, you might say put all the alarm data into a buffer and then log later when you've got a few more CPU cycles or disk time to be able to log the data, rather than trying to log everything every time it comes up. You can also let the database server handle some of the calculations. So alert, for example, average, sum, minimum, maximum, they can be performed faster in the database server than in some applications, especially if you've got large amounts of data. The database engine itself is optimized to do some of these functions. It might also be easier to implement an application rather than hard coding it. So if you wanted to do, for example, a VB.NET or Python script to do an average, you'd have to read all of the data from the database. You'd then have to add it all up, and you'd then have to divide by the number of values there are, and that could be quite a big calculation. Whereas you might already be able to get the average function from the database, and the database engine can do that much more quickly for you. It might also be, if you're going to be doing the averaging or minimum or maximum calculations a lot, store that data in the database at the time when you're storing. So that way it will be very quick to retrieve, because you won't have to do a calculation. It will already be there in the database. So there's a lot of things you can do to tweak how your application runs just by looking at the types of data and optimizing the data you're storing. But probably I'd start with indexing. That's probably a good one to start. And then check the specifics for your database, and then have a look at the sorts of things you're doing with maybe column names and data types and so on. And there might be no single fix, but if you could do 5 fixes and each of those fixes includes database performance by 5%, then that's 5% 5 times. That's a good way of improving it. You haven't done one single thing, but you've done lots of things to overall improve the performance. So moving on again, let's look at backups and archiving. Backups and archiving are actually different. Generally, a backup is a copy of important data in case of a hardware failure or software corruption. So a backup is something you want to do frequently because between the time of the failure and your last backup, you could potentially lose all of that data. Again, with databases, it's a bit better because you could do like a weekly backup, and then you could do an hourly backup of a transaction log. So that might help you, but you could end up with a lot of files to manage there. If you do your backup once a week, then you've got your main backup, and you could end up with a week's worth of transaction logs. If you've got an hourly transaction log, the good news is you'll never lose more than an hour's data, but when you rebuild the database, you could have up to a week's worth of transaction logs. So 7 by 24 number of transaction logs, so there could be quite a bit of work to recover your data. So that could affect how quickly you can recover that data and get back up and running again. But backing up is important. An archive is slightly different. An archive is long-term data storage of important data which you might need to retrieve in the future, or you might just be keeping just in case. So for example, let's say you're running the operations in a car plant. Your key operational metric is you keep data for 30 days because you want to make sure your machines are running efficiently, and you need to be able to go back over up to 30 days to check if anything went wrong. So that's your sort of data that you need to think about backing up. That's your important data. However, at the same time, there might be operational data that you keep for longer periods for operational reasons. So maybe, for example, in a car, you need to keep a track of all the serial numbers of the tyre you fitted to that vehicle, because those tyres might be used in case there's a warranty claim, and you have to go back to your vendor for those tyres if that tyre wore out earlier and there's a warranty claim by whoever you sold that vehicle to. So that might be archived data. It's important data, but you don't need to access it for operational reasons unless something goes wrong in the future. So there is a difference between how you handle backups and archiving. What is the exact difference? Well, again, that's going to depend on your application. Some people will back up everything and keep years worth of data. That's fine. Some people will say, I only want a year's worth of data because I don't want to spend too much on disks. and I'll archive anything older than that to tape. And then if they need to get it out, they have to go and find that year's tape, and they have to restore the data from that tape and do it that way. But it's harder then. But again, it's how often do you need that data? How easy does that data need to be retrieved? And how often are you going to need to retrieve it? If you're really worried about data integrity and uptime, you can also consider redundant servers for hardware and software. So for example, with Microsoft SQL Server, you can run that in a cluster, which is a set of computers where one can take over if one fails. You've also got the option of replication of a database, so you can have your data spread across multiple databases. If one fails, the other one can take over. So again, you've got to think, how do you handle your critical data? Only you can decide if your data is critical. If there's a warranty claim on a tyre from 10 years ago, well, if you haven't got that data, okay, it's maybe cost you a tyre. Or maybe you just go back to that user and say, sorry, we haven't got that data anymore, and you come to some sort of arrangement. But that data maybe isn't critical. But if it's something more important, then you have to think about that data, is it critical? Maybe it's data, for example, you've maybe got some sort of process you run, and out of that process you dump the effluent into a local river, so you need to keep records for that data to say that effluent you dumped was clean enough and met the local environmental standards. So that's quite critical data, because potentially if you don't have that data, you could be liable for some sort of penalty or possibly a big fine, ranging up to legal penalties where people could end up going to prison. So I would consider that sort of effluent type data critical data. So again, part of it is about that previous slide. Is it archival data, or is it critical data you want to keep online? But regardless, you've then got multiple options. So we mentioned redundancy. You can replicate your databases. You can have redundant networks and servers. Within a single computer, you could consider RAID disk arrays. These days, I would say RAID is probably not that important. I think it still has an effect on disks, particularly hard disks with databases, because you might be using a rotating hard disk, and RAID is a way of both increasing the performance of the disk, but also increasing its reliability. But I'd say as soon as you go to an SSD, RAID doesn't really make any sense, because SSDs are already orders of magnitude more reliable than a rotating hard disk. And they fail or tend to fail more gracefully. Not always, but you're more likely to be covered by your backup strategy than having to rely on RAID disks, because they do tend to be more reliable. Some people do use RAIDs with SSDs, but again, that's something you'd have to investigate to see if that's a good idea or not. But more likely, I would say if you're really worried about your data, use database replication with SSDs for performance. And SSDs are in some ways more reliable than rotating disks, like I mentioned. No rotating hardware bits, no chance of seizing up, more shock and vibration. Temperature's another thing. Typical rotating hard disk is 0 to 40 degrees C, whereas an SSD can go minus 40 to plus 85 if you use the right level. So again, lots of things to consider there. Store and forward is another aspect. A lot of people are collecting data on one node, but logging it to another on a different node. So your database collection is being done on, say, a HMI SCADA computer, but your database server is a different computer. So what you might want there is a store and forward mechanism where you buffer data at the collection point. So the idea of this is you store the data locally and then you forward it to the database. If the database isn't there or the network fails, you continue to store it locally, and then when the database or the network connection recovers, you then forward that data. So that's often handled automatically by certain applications. For example, your HMI SCADA, it may store the data locally as an XML file and then offload that data back onto the hard disk when it recovers. Or it might be something you do at the application level by looking at the hard disks, and if a hard disk fails, you would then do some sort of logging of the data then in your local application. So several ways of doing that. And of course, ultimately, don't forget you've got to keep backups and look at your backup strategy. Two things you need to do there. One thing is keep multiple copies and keep them off site. If your site is flooded, it doesn't matter that you've got a backup. If you can't get to the site, the backup is gone. And another thing is test your recovery process. I've heard of people using the same tape for their backup. They've never trusted they could recover the data. When they did have a failure, they went to the tape and they found the tape wore out many write cycles ago. Effectively, the tape was clear because the magnetic media had been stripped off. So make sure you regularly test your recovery process. A backup that you can't recover is not a backup. It's just a waste of time and money. So yeah, backups are also very important for critical data, but also for that archiving data as well. So again, your archiving might use a similar sort of process, multiple backups, multiple archives, test it off-site, and test that you can still recover your data. Now for a small HMI SCADA application, you may be logging a few gigabytes of data, but it's not too important, so you don't have to worry about the storage implications. But as your application grows, if that data becomes more important to your operations, maybe that data is critical for warranty purposes or for regulatory purposes, then you may have more and more data you need to store. Of course, if you've got more machines, a larger process, lots of data ends up meaning, of course, lots of disk space required. My recommendation is still use SSDs. The bigger SSDs do cost more, but not that much. Compared to enterprise hard disks and RAID, if you need 2 rotating hard disks or 3 rotating hard disks or even 4, then you're probably approaching the cost of using an SSD, and the SSD can often be more reliable and easier to manage. So definitely think about SSDs, but if you've got too much disk storage, then maybe rotating hard disks still have their place. And the same with backups as well. Think about how your backup works. Are you archiving to disk? Are you archiving to tape? What are you doing there? Something you can do to reduce the amount of disk space you need is optimizing writes with deadbanding. So some people log every single item of data that comes in, but if you're logging something like a tank level, you may find that there's a lot of ripple on that tank level. The tank level is actually, say, it might be 60% plus or minus 1%, and that ripple of 1% is happening frequently. So what you actually end up doing is, if you write every time it changes, you're logging 61, 60, 59, 60, 59, 60, 61 and so on, when actually the average tank level over that period is actually 60. So you could optimize the storage by logging data when it only changes by more than a certain amount. So you might set your deadband at 2%. So now instead of logging those 5 values, you'd just log one value of 60, and only when it changes to 58 or 62 would you actually log a new value. So good way of optimizing writes, reducing the amount of disk space used, reducing the amount of storage you have to perform. Another thing you might want to do is summarize data at regular intervals. Okay, so maybe it's important that you know that it's at 60% for that particular instance, and maybe that's important if you're running a trend over the next hour. But once you get to a few days onwards, you might not need all of those individual logs. You might just want to know that for that hour, the average tank level was 60%. So you might not want to know what it was every single second or every single minute. You might also then summarize by saying, well, this is the average. Over that hour, the average was 60%, the maximum was 63, the minimum was, say, 54. So you might want to do it that way as well. So you're only storing 3 values instead of, say, 60 values, one for every minute or so. So there are lots of ways you can summarize if you don't need every single data item for that ongoing analysis. You could do that per hour, per shift, per day, per batch, per week, per month, and so on. Typical summary, as I say, would be minimum, maximum, and average, but there might be other values you might need. Maybe you only need the average. And then again, to reduce your storage, archiving. Archiving old data to archival storage, it's slow because you might even have to have a manual process where you have to send someone to an archive site to retrieve some physical media. So you might be looking at, hours of latency in terms of getting that data, but it's still there if you really need it. So again, you have to think about your data. How much data do I need? What's important now? What will be important in a week's time? What will be important in a month's time? What will be important in a year's time? And you manage your data accordingly. So if you want to read more about SQL, then I recommend going to these particular websites here. So there's the W3 or WWW Schools SQL tutorial. So that's that website there. That's pretty generic and covers common databases. but it's a good way of finding out more about all of the standard SQL queries that are available. If you're using Microsoft's SQL Server, then you can go to learn.microsoft.com and you can look at the Transact SQL reference. That, of course, is specific to Microsoft's SQL, and you also need to think even there about which SQL Server version you've got, as sometimes for syntax changes, not every command is available in every version of SQL Server, and sometimes the command syntax changes from one version to another. So a bit more complicated, but certainly if you're using SQL Server, then that's the reference where you need to go. So I've covered databases that use structured query language. There are some databases which don't use SQL. They're called Non-SQL Databases or NoSQL, and these are alternatives to SQL databases that don't use a structured query language. Some of them still do support structured query languages, but the idea is these might use different storage mechanisms with different retrieval mechanisms, and then they allow you to retrieve and analyze the data using different mechanisms. So for example, rather than use an SQL query and a complex analysis application written in, say, VB.NET or Python or whatever, you might use something like R. So R is a language which can do data retrieval and analysis using these potentially non-SQL type data. So alternatives include a key value pair. They might include wide columns with variable row formats. It might be a document. This is sort of a subclass of the key value pair, and it might require metadata within that document. Another option is graphing, where you add links or relationships between documents. So these are very different to that idea of SQL queries, often used in large database applications like data lakes, and often used where the data is a lot less unstructured or less structured than SQL data, but where the data is still meaningful. So other options here are those NoSQL type databases. Some of these trade consistency for performance. It could be that sometimes if you're logging multiple key value pairs, for example, you might not get that consistency of data. Depending on what your database is doing, that may eventually catch up, but it might take some time. But these NoSQL databases are very good for high-level analysis and maybe also for working with machine learning and artificial intelligence type techniques as well. So they do have their uses, but they are often very different to the SQL type databases that we've looked at previously. So I also want to specify the differences between a database versus a historian. A historian is a type of database, but if you look at it in detail, then the way to differentiate them is that the RDBMS has multiple tables in a relational format. That's where the name comes from, relational database. And it can be used for any application. So CRM, ERP, data logging for HMI SCADA, maintenance management system, multiple uses. What's important about a typical RDBMS is that data integrity is key, using that ACID technique that we mentioned. But one issue of these RDBMSs is they're not optimized for time series data. So this is where a historian comes in. A historian is a special version of a database optimized for time series data. They're intended for high-speed data logging and retrieval. And often if you look at those ones I mentioned, OSIPy, GE Historian, AspenTech IP21, they are intended for industrial data that is logged at specific intervals, like every millisecond, every second, or so on. The stored value accuracy is important, but the overall integrity of the data less so. You often find with these big historians, it's okay to miss values because maybe the data's bad. It could be that when your gas turbine is starting up, okay, maybe you're not worried about the data at that startup time, you're worried about it when it's running. It might be that your data collection device was disconnected and during that time the data's bad because there is no data. So it's important that the value you have is accurate, but the overall integrity of all of the data isn't that important. Whereas in a large database, all of the data is important. You might not think so, but imagine if a bank didn't have 100% integrity, then that could be your bank account that's affected. You wouldn't be very happy. Whereas if you're storing data for a gas turbine, if you've got a few missing bits of data here and there, not such a problem. So what a historian does is it does a couple of things. It stores possibly using compression to reduce disk space. That also increases efficiency, and they're often much faster than those relational databases, but for time series data only. Bear in mind your application may require both. You might want a relational database for alarms and events and a historian for time series data. In that case, it's important that you need to be able to link those two databases. The easy way of doing that is with a timestamp. So you might say for this particular alarm, which occurred at say 12 o'clock, your SQL query might do something like, let's retrieve the historian data between 5 to 12 and 12 o'clock to find out what happened before the alarm. And then you might also want to look at what happened 5 minutes afterwards for your post-trip analysis. So you're combining there the alarm and event data with that time series data. In that case, it's often done via a combination of the timestamp, but also maybe you'd be looking at the tag names as well, because you want to look at the important data. So I'll leave you with this database comparison. There's no right or wrong database. It's going to depend a lot on how scalable you want your database to be, how much money you can afford, and also other aspects of maybe what you've used before. Do you want to pay per server or per client? Do you want a cloud-based database? Does your organization have a particular preference? Do you want to focus on alarm and event type relational data, or do you want to focus on time series data? So there's a lot of different aspects there as to which you would choose. It is possible to migrate from one tool to another. How you do that, you'd have to look at what your particular database is. Many databases do support export to XML and import from XML or CSV type format. So it is possible to change databases, but if you're going to do that, that could be quite a major exercise. And of course, you'd also need to look at then, if you are migrating from one database to the other, how much work do you need to do with your SQL database queries? Do you need to update your queries? Do you need to check your database formats? Do you need to have compatible column formats? So it's much easier if you can to start with the database you're going to end up with, but it is possible to convert over time if you need to.